GIS Fundamentals, Section 14, Data Standards and Data Quality. A standard is an established or sanctioned measure, form, or method. It is an agreed-upon way of doing, describing, or delivering something. Spatial data and analysis standards are important because of the range of organizations producing and using spatial data, and because these data are often transferred among organizations. GIS practitioners use several types of standards. Data standards are used to format, assess, document, and deliver spatial data. Interoperability standards identify how spatial data are served between heterogeneous networks of software and hardware systems, for example, between wireless mobile devices and shared databases. Analysis standards ensure that the most appropriate methods are used and that the spatial analysis provide the best information possible. Professional or certification standards establish the education, knowledge, or experience of the GIS analyst, thereby improving the likelihood that the technology will be used appropriately. The Federal Geographic Data Committee, FGDC, is the leading government organization in the United States in defining data standards. The FGDC focuses on the National Spatial Data Infrastructure, or NSDI, in the United States, a set of resources to aid the creation and sharing of digital geographic data. The International Standards Organization, or ISO, organizes international standards and sponsors the ISO/TC 211 standards. These specify ways to store and represent spatial and related information, services and data management, processing, transferring, and presenting information. Spatial data sharing, particularly in real time, is supported by system interoperability. The Open Geospatial Consortium, or OGC, is an ad hoc, self-selected group of companies, research institutions, government bodies, and individuals dedicated to developing interoperability standards. Web mapping services, WMS, standards are an example of OGC initiatives. Web mapping services allow GIS software to access data across the Internet as if they were stored on the local hard disk. A GIS program or utility maps the WMS to the local computer, meaning it may access the data with the same protocols as if it were stored locally. Web services such as WMS are important for the future of cloud-based computing, where data, programs, and processing is seamlessly distributed on computers connected across the web. Cloud-based geospatial computing is inherently dependent on robust, well-defined interoperability standards such as those being developed by the OGC. There has been recent progress on the development of a basic set of standards in the professional practice of GIS in the United States. Known as competency models, they define a set of skills considered essential for effective work in a field and have been developed for a growing number of industries. The Geospatial Competency Model. The Geospatial Technology Competency Model identifies a set of core and industry sector geospatial abilities. The competency model identifies examples of over 40 critical work functions geographic technology professionals are commonly expected to master and use in their careers, and the background knowledge on which these critical work functions are based. The geospatial competency model is based in part on the geographic information science and technology body of knowledge, first published by the Association of American Geographers in 2006. Critical work functions include operations in basic geodesy, data collection systems, data structures, GIS operation and programming, analytical methods, cartography, the place of geographic information science and technology in society, and organization and institutions. A set of higher-level requirements are noted for specific occupations. Spatial data standards. Spatial data standards can be defined as methods for structuring, describing, and delivering spatially referenced data. Spatial data standards may be categorized into 4 areas: media standards, format standards, accuracy standards, and documentation standards. Media standards refer to the physical form in which data are transferred. They define specific formats for CD-ROM, magnetic tape, optical or solid-state storage, or some proprietary drive or other media type. Standardized formats are specified by the International Standards Organization, or ISO. Format standards specify data file components and structures. The U.S. government supports the Spatial Data Transfer Standard, or SDTS. This format specifies the logic, format, and encoding for raster, vector, and topological data transfer of spatial data. Esri shapefiles are a cluster of files including .shp, .shx, and .dbf, and are a commonly supported vector format, and many organizations transfer data using them. Image files in a .img format were first developed by ERDAS, ERDAS, an early remote sensing software package, and are widely supported, and Esri geodatabases are becoming a common form of data delivery. Spatial data accuracy standards document the quality of the positional and attribute values stored in a spatial dataset. Documentation standards define how we describe spatial data. Data documentation standards are an agreed-upon way of describing the source, development, and form of spatial data. There are many ways to describe data quality, including the average distance error, the largest distance error, the percentage of points that are above an error threshold, or the total area that is misclassified. Attribute error may also be described in many different ways. The producer may describe the spatial data quality in one manner, but this may not allow a user to judge if the data are acceptable for an intended application. Data accuracy. An accurate observation reflects the true shape, location, or characteristics of the phenomena represented in a GIS. When the concept of accuracy is applied to spatial variables, it is a measure of how often or by how much our data values are in error. Accuracy may be reported as a frequency. For example, when we report that 20% of the land cover class labeled as cropland is actually perennial grasses. Alternatively, accuracy may be expressed as an average error magnitude. For example, light poles may be displaced on an average by 12.4 meters from their true locations. Errors can be caused by how we conceptualize the features, our methods of data collection and analysis, human error, or data may simply be out of date. Documenting spatial data accuracy. Establishing the accuracy of a dataset requires we know the accuracy of our measure of truth. There are 4 primary ways we describe spatial data accuracy: positional accuracy, attribute accuracy, logical consistency, and completeness. These 4 components may be complemented with information on the lineage of a dataset to define the accuracy and quality of a dataset. Positional accuracy describes how close the locations of objects represented in a digital dataset correspond to the true locations for the real-world entities. Attribute accuracy summarizes how different the attributes are from the true values. Logical consistency reflects the presence, absence, or frequency of an inconsistent data. Logical consistency may also be applied to the attributes. Completeness describes how well the dataset captures all the features it is intended to represent. Lineage describes the sources, methods, timing, and persons responsible for the development of a dataset. Knowledge about certain primary data sources helps define the accuracy of a dataset. Accuracy is most reliably determined by a comparison of true values to the values represented in a spatial dataset. Positional accuracy. Positional accuracy measures how close a database representation of an object is to the true value. Precision refers to the consistency of a measurement method. Precision is usually defined in terms of how dispersed a set of repeat measurements are from the average measurement. A precise measurement system provides tightly packed results. Precise digitizing means we may repeatedly place a point in the same location. A set of measurements may be precise but inaccurate. Repeat measurements may be well clustered, meaning they are precise, but they may not be near the true value, meaning they are inaccurate. A bias may exist, defined as a systematic offset in coordinate values. A less precise process will result in a set of points that are more widely spread. However, their average error may be substantially less. Therefore, the set is more accurate. The mean error and an error frequency threshold are the statistics most often used to document positional data accuracy. We may compute the mean error by summing the errors and dividing the sum by the number of observations. This gives us our average error, a useful statistic somewhere near the midpoint of our errors. We are often interested in the distribution of our errors, and so we also commonly use a frequency histogram to summarize our spatial data error. The graph will indicate the largest and smallest errors and also give some indication of the mean and most common errors. The mean error value does not indicate the distribution or spread of the errors. Two datasets may have the same mean error, but one may be inferior. The dataset may have more large errors. The bottom graph in figure 416 has the same mean error, 13 meters, as the top graph. The errors have a narrow distribution, meaning the errors are clumped closer to the mean than in the top graph, where there are fewer large errors. Because the mean statistic alone does not provide information on the distribution of positional errors, an error frequency threshold can be reported. An error frequency threshold is a value above or below which a proportion of the error observations occurs. If we are concerned with the frequency of large errors, this may be a better summary statistic than the mean error. A standard method for measuring positional accuracy. The Federal Geographic Data Committee of the United States, or FGDC, has described a standard for measuring and reporting positional error. This standard is known as the National Standard for Spatial Data Accuracy, or NSSDA. The NSSDA specifies the number and distribution of sample points when performing an accuracy assessment, and prescribes the statistical methods used to summarize and report positional error. There are 5 steps in applying the NSSDA. 1. Identify a set of test points from the digital data set under scrutiny. 2. Identify a data set or method from which true values will be determined. 3. Collect positional measurements from the test points as they are recorded in the test and true data sets. 4. Calculate the positional error for each test point and summarize the positional accuracy for the test data set in a standard accuracy statistic. 5. Record the accuracy statistic in a standardized form. GNSS are a common source of truth, and digital orthophotographs and field surveys are also a common source of truth. The NSSDA specifies between 20 and 30 well-distributed test points. Test points should be distributed as evenly as possible throughout the data layer to be tested. Each quadrant of the tested data layer should contain at least 20% of the test points, and test points should be spaced no closer than 1/10 the longest spanning distance for the tested data layer. Accuracy calculations. The calculation of point accuracies and summary statistics are the next steps in accuracy assessment. First, the coordinates of both the true and data layer positions for a feature are recorded. These coordinates are used to calculate a positional difference, known as a positional error, based on the distance between the true coordinates and the data layer coordinates. The squared error differences are then calculated, and the sum, average, and root mean square error statistics determined for the dataset. The root mean square error is not the same as the average distance error, nor a typical distance error. The root mean square error is a statistic that is useful in determining the probability thresholds for error. The root mean square error is related to the statistical variance of the positional error. The root mean square error tells us something about the distribution of distance errors. A large root mean square error means the errors are widely spread, and a small root mean square error means the errors are packed tightly around the mean value. Statistical theory allows us to establish fixed numbers that identify error thresholds. When we fix a 95% error threshold, this means we identify the specific number such that 95% of our errors are expected to be less than or equal to the threshold. Statistical theory tells us that when we multiply the root mean square error by the number 1.7308 and assume a Gaussian normal distribution, we obtain the 95% threshold. Errors in linear or area features. The NSSDA treats only the accuracies of point locations. There are no established standards for describing the accuracy or error of linear or area features. An epsilon band can be used to characterize uncertainty in line position. An epsilon band may be defined as a region near a line that has a very high probability of containing the line. The epsilon band may be thought of as having a high probability of encompassing the true line segments. Larger epsilon bands are associated with poorer quality data. Nodes or vertices may be used as test points, provided they are well defined and the true coordinates are known. Attribute accuracy. There is no national standard for measuring and reporting attribute accuracy. Accuracy for continuous variables may be calculated in an analogous manner to positional accuracy. Accuracy for each observation is defined as the difference between the truth and database values. A set of test data points may be identified the true attribute value determined for each of those test data points, the difference calculated for each test point, and the accuracy summarized. The accuracy of categorical attribute data may be summarized using an error table and associated accuracy statistics. Error tables, also known as error matrices, confusion matrices, and accuracy tables, are a standard method of reporting error in classified remotely sensed imagery. An error table summarizes a two-way classification for a set of test points. A categorical variable will have a fixed number of categories. These categories are listed across the columns and along the rows of the error table. Each test feature is tallied in the error table. The true category and the value in the data layer are known for each test feature. The test feature is tallied in the error table based on these values. The true values are entered via the appropriate column, and the data layer values are entered via the appropriate row. The table is square because there is the same number of categories in both the rows and columns. Correctly classified features are tallied on the diagonal. The true value and data layer value are identical, so they are noted at the intersection of the categories. Incorrectly assigned category values will fall off the diagonal. Per category accuracy may be extracted from the error table. Two types of accuracy may be calculated: a user's accuracy and a producer's accuracy. The user relies on the data layer to determine the category for a feature. In effect, the user wants to know how many features that are classified as a category, the row total, are truly from that category, the diagonal element for that row. The user's accuracy is defined as the number of correctly assigned features, divided by the row total for the category. The producer, on the other hand, knows the true identity of each feature and is often interested in how often these features are assigned to the correct category. The producer's accuracy is defined as the diagonal element divided by the column total. Error propagation in spatial analysis. Input error affects output values. Several approaches have been developed to estimate the impacts of attribute errors on spatial models. Rather than trying to identify how errors in the input propagate through to affect the final model results, we may opt to perform an error assessment of our final output. Error propagation in spatial models is often investigated with repeated model runs. We may employ some sort of repeat simulation model that adds error to data layers and records the impacts on model accuracy. These simulation models often employ a standard form known as a Monte Carlo simulation. The Monte Carlo method assumes each input spatial value is derived from a population of values. For example, land cover may range over a set of values for each cell. Further, model coefficients may also be altered over a range. In a cartographic model, the weights are allowed to range over a specified interval when layers are combined. A Monte Carlo simulation controls how these input data, or model parameters, are allowed to vary. Typically, a random normal distribution is assumed for continuous input values. If all variables except one are held constant, and several model runs performed on different random selections of the variable, we may get an indication of how a variable affects the model output. A Monte Carlo, or similar simulation, is a computationally intensive technique. Thousands of model runs are often required over each of the component units of the spatial domain. The computational burden increases as the models become more involved and as the number of spatial units increases. GIS Fundamentals, Section 14, Data Standards and Data Quality, Section Summary. Data standards, data accuracy assessment, and data documentation are among the most important activities in GIS. We cannot effectively use spatial data if we do not know its quality, and the efficient distribution of spatial data depends on a common understanding of data content. Data may be inaccurate due to several causes. Data may be out of date, collected using improper methods or equipment, or collected by unskilled or inattentive persons. Accuracy is a measure of error, a difference between a true and represented value. Inaccuracies may be reported using many methods, including a mean value, a frequency distribution, or a threshold value. An accuracy assessment or measurement applies only to a specific data set and time. Accuracy should be recognized as distinct from precision. Precision is a measure of the repeatability of a process. Imprecise data collection often leads to poor accuracy. Standards have been developed for assessing positional accuracy. Accuracy assessment and reporting depend on sampling. A set of features is visited in the field and the true values collected. These true values are then compared to the corresponding values stored in a data layer, and the differences between true and database values quantified. An adequate number of well-distributed samples should be collected. Standard worksheets and statistics have been developed. Data documentation standards have been developed in the United States. These standards, developed by the Federal Geographic Data Committee, are known as the Content Standard for Digital Geospatial Metadata. This standard identifies specific information that is required to fully describe a spatial dataset.